Welcome back. So in the previous session, we derived and defined the Moivre's theorem and also stated the formula for finding the nth roots of a complex number. So in this session, we are going to see how to apply the Moivre's theorem on finding the powers of complex numbers and their respective roots. So let's begin with examples. So begin with an appetizer. So express the number cos 9 pi over 17 plus I sine 9 pi over 17, everything raised to power 5 divided by cos 2 pi over 17 minus I sine 2 pi over 17. This one is raised to power 3 in the form A plus B I. So this is what we have as our complex number. So solution. So we can let Z1 be cos 9 pi over 17 plus I sine 9 pi over 17. I remember this power is 3. So Z1 power 5 will be given by cos 5 times 9 pi over 17 plus I sine 5 times 9 pi over 17. So just applying the Moivre's theorem that states that Z power n is R power n into cos n theta plus I sine n theta when Z is given by R cos theta plus I sine theta. So that's the definition. So in our case, R is 1. So that's why we just have this as our expression. So this will give us Z1 power 5 equals to cos 45 over 17 pi plus I sine 45 pi over 17 and you can as well write this one as Z1 power 5 is actually e raised power 45 pi over 17 I, because remember the exponential and polar form actually, they are more or less the same structures in terms of the description. And when you put in the exponential, then it will make our simplification of the numerator and denominator much easier to deal with. And then denominator, let it be Z, let's say Z2 be cos of the number of 2 pi over 17 minus pi sine 2 pi over 17. So this can be written as cos minus 2 pi over 17 plus I sine minus 2 pi over 17. So that we have the structure cos theta plus I sine theta. So Z2 power 3 will be cos 3 times minus 2 pi over 17. Submit. So sorry for that small delay. So we have plus I sine 3 minus 2 pi over 17. So this will give us cosine of minus 6 pi over 17 plus I sine minus 6 pi over 17. And then it is easier when the number is in exponential form. So we write this one as e raised to power minus 6 pi 17 I. So Z1 power 5 over Z2 power 3 is e power from the first one is 45 over 17 pi I divided by e power minus 6 pi over 17 I. And then this just will use the loss of indices. So this will give us e power 45 over 17 pi I minus minus will be plus 6 pi over 17 I. 45 plus 6 is 51. 51 divided by 17 is 3. So I'll have e power 3 pi I. And then when you have e raised power 3 pi, you can always change this into polar form as cos 3 pi I, 3 plus I sine 3 pi. So this is the same number as e raised power 3 pi I. Then using your calculator, 3 pi is 3 times 180, so 180 times 3, 540, so cos of 540 is minus 1, plus sine of 540 is 0. So that will be our complex number. Then another example. Simplify one plus I power 18. So when you are given such a complex number, first thing you change it into the polar form. So you say let z be given by 1 plus I. So modulus of z, which is r, of the square root of 1 squared plus 1 squared, which is root 2. And then you find the argument. And before you find the argument, remember you have to sketch the number to know in which quadrant it lies. And this number will be in this first quadrant. So when you define a right angle triangle here, so this will be 1 unit, this 1 unit. So theta, which is the same as argument of z, will be simply tan inverse of y, which is 1, over x, which is 1. So tan inverse of 1 is pi over 4, or you can say 45 degrees. So in polar form, z equals to 1 plus I will be equals to r, which is root 2, into cos theta, which is pi over 4, plus I sine pi over 4. Then applying the Moivre's theorem, we have 1 plus I power 18, the same as root 2 into cos pi over 4 plus I sine pi over 4. You raise this number to 18. And so by the Moivre's theorem, this means root 2 would be raised to power 18. And then cos, then these angles are multiplied by 18. So 18 times pi over 4 plus I sine 18 times pi over 4. So root 2 raised power 18, we get 512. Then 18 divided by 4, we get cosine of 9 pi over 2 plus I sine 9 pi over 2. So when we define cos of 9 pi over 2 is 0, plus sine of 9 pi over 2 is just 1. So multiplied by I, you get I. So this will be simply 512 I as our final answer. And then example 2. Express 1 plus I root 3 power 7 in the form x plus yi, where x and y are real numbers. So actually we do it like in the previous question, express in polar form and then apply the Moivre's theorem. So I hope you have tried it out. So the key thing is to ensure that you put the number So the key thing is to convert the number in polar form. So first, let z be 1 plus I root 3. So r, which is the same as modulus of z, will be 1 squared plus root 3 square. So it gets the modulus is 2. Now this number is actually in the first quadrant, where this is the root 3 and this will be 1. So then it's very easy to determine the argument, of z. So argument of z is simply theta, which is tan inverse of root 3 over 1. And when you determine the tan inverse of this, you get 60, or the same as pi over 3. So argument is pi over 3. So which means that z is the same as 1 plus I root 3 is the same as 2 cos pi over 3 plus I sine pi over 3. So z power 7 will be we are raising this number to power 7. So the Moivre's theorem gives 2 power 7 and then cos 7 times pi over 3 plus I sine 7 times pi over 3. So it will be 2 power 7 into cosine of 7 pi over 3 plus I sine 7 pi over 3. Now 2 power 7 is 128. So this will be 128 into cosine of pi over 3 is a half, 7 pi over 3 is a half. And then sine of 7 pi over 3 is root 3 over 2. So when you multiply by 128, we get 64 plus 64 root 3 I. So this will be the answer to that given problem. Then lastly, simplify minus root 3 plus 3I power 31. So what you do, you change the number in polar form. So you let z be minus root 3 plus 3i. Then r would be modulus of this number, which is square root of minus root 3 squared plus 3 squared. And when you work out this, you'll get this will be square root of 3 plus 9, which is square root of 12, which is 2 root 3. And then you need to get the argument, and this number is in the second quadrant. If I call this one alpha, note that this will be the argument, which is theta. So here, their change in y, or the number of units along the imaginary axis, there are 3. Number of units along the real axis is root 3. So alpha is the same as tan inverse of opposite is 3, of adjacent is root 3. So 3 divided by root 3, then tan inverse of that answer is 60 degrees, which is pi over 3. So if alpha is pi over 3, then theta, which is the argument, will be pi minus pi over 3, because the whole of this angle is 180 degrees. So this will give me 2 pi over 3. So now we can write z in. So z is given by r, which is 2 root 3 into cosine of 2 pi over 3 plus I sine 2 pi over 3. So then now when it comes now to raising to power 31, then z power 31 would be 2 root 3 raised to power 31, and then cos 2 pi over 3 times 31 plus I sine 2 pi over 3 times 31. And when you work out this, you'll get 2 root 3 power 31 into cosine of this number will give you minus a half, confirm, plus cosine of this one will be square root of 3 over 2i. If you wish, you can simplify this and then multiply by each term to get the final result. So the next session will be doing examples involving the roots of complex numbers, which is also another application of the Moivre's theorem.